Hi, I'm Andrew Armstrong and welcome to the Back Office Teardown Lab. You can see it's a different setup today. It's a bit like my streaming setup, and that's because I need my PC to show you something instead of my hands. So I'm going to be playing with our Odroid, and this is the one I actually modified to have headphone output right there. See the old headphone output? Check out that video if you haven't. It's a really good mod. Now you can see on the screen that's your odroid-go. When I posted the video about the headphones, a lot of people asked, let's go through the schematic. So Andrew, can you go through the schematic? And yes, I can, because I was going through it this morning because I was trying to do a solderless mod for the headphone, something that you could plug into the top here. But at the moment, it's a little bit too much work. We have to put a SPI digital to analog converter that will just plug in there and do it. And it's like, I can do it, but I'm almost getting bored of designing it now. Like, do I want to? Are there anybody out there who actually really want to buy this? Is it worth the time? So please comment down below, though, if you think a solderless headphone upgrade would be interesting to you. And if enough of you say yes, maybe we'll just go and design that and get on with it. But it does allow me to go through this schematic a little bit with you. So if you look here at github.com/hardkernel/odroid-go, you will find, going through there, a folder called Documents, and inside the documents you'll find a schematic, and it looks like that. And then what you need to do is download that and you get this PDF. So there you go, there's a PDF right there, and I'll try to remember to put a link down below to the GitHub, but you can find it. And fortunately I can zoom in, because it's a PDF, it does retain all of the zoominess. So what I'm going to do though is just a very quick high level. We'll just run through the main building blocks of an Odroid if you're going to build one from scratch. And by the way, you could copy this, you could literally build your own Odroid from scratch, odroid-go, because it's not very complicated. And as we go through, you'll see there's some things I don't like about this design that they could have done better. Anyway, let's start off top left. You have the V-bus, that's your USB coming in, and then you've got your power supply going to your amplifier. This is your sound out here. And then moving to the right, this is your external I/O header, and some interesting things there. That's sort of buffering. I need to check that out. We have our Dpad, and then we have our LED down here, bottom left corner. There are your buttons, menu, volume, select, start. There's the buttons there. And then on the bottom right, that's your LCD screen. So nice and simple on that one. The next page is even simpler because it's your two main ICs. So you have your USB to UART IC, which is pretty big. And I'm kind of surprised they need one, but we'll go through that, why that's there. And then you have your main module. And it's tiny, this thing. You can see it's only got, I can't really count the pins, 38 pins. Very small. Pretty good for what it does. Then you have your DC to DC converter, so that gets you the power from all the different sources to feed your module. And finally your battery charger. So, oh, I said finally your battery charger, and then finally your TF card slot. So that's the slot on the back which takes your micro SD. So let's start here with the V-bus. We're going to sort of scroll around, so I do apologise for moving around. So you have here micro USB ports. You'll see V-bus, that's the power coming from the USB. And then you've got a bunch of grounds. So one of them is the ground pin, and then you've got two ground pads normally. If you look at a USB connector, you have that metal bit on the outside, and it's soldered to the PCB to hold it down. So when you shove your USB in, it doesn't break. That's those additional grounds here. And D- and D+ is the data. That's the data coming from the USB. And every now and then you'll see these blue blobs that say TP. Those are test points. So in testing, when they made this, you can actually solder to those blobs and then look at what's coming in off the USB bus so you can measure. Always handy when you make your designs to put in test points. Now, interestingly, we analysed the output of the module a little bit because I wanted to do something with the sound, as I suggested earlier, but I couldn't do it because IO25 and 26 is multiplex. So not only is it the I2S output, which is the sound, audio streaming sound, digital sound output, it's also, there's a built-in digital to analog converter inside the unit, and those are the two pins for the digital to analog converter for the differential signal. So it does have a DAC in it, but unfortunately it's only routed to the speaker, so it means we can't make a solderless upgrade right now. And even if we do make an upgrade, it will, that is solderless, like something you can plug in. It does mean you'll still have to drill a hole and stuff to actually get your DC, your headphone jack in there. So this is the PAM 8304 amplifier, so it's a single channel amplifier, and you can see it's real nice and simple. You have a differential signal coming in on pins 4 and 5. I still haven't checked out what SD means. It's just normally probably a reset or a standby detect. So IO25 can control the standby detect. And actually it's interesting because you see IO25 is also one of the differential inputs. So it probably, once it starts twiddling, it probably just keeps it on basically. It probably has, like, if it doesn't see anything on that pin for a few seconds, it turns off. So it's kept alive by that. Then VDD and PVDD are powers coming in. There's probably two different inputs for power, because you probably have one for analog and one for just sort of board power. And the reason is, if you have noise issues, you might have a separate analog power source, something like that. And then your output is also a differential output, which drives each side of the speaker. And there you see it right there. Pins 1 and 2, and this is test point 1 and 2, which we soldered to last time. So that was because I had surface mount components to do our headphone mod. If you don't have surface mount components, you've got through hole, which would be great. You can actually make that little resistor circuit on the headphone jack itself, and you could even put wires and plug straight into pins 1 and 2 and not do any of the messing around on the actual motherboard. That's probably better for you home hobbyists. So next we have our external I/O header here, and it's a bit interesting because I was trying to figure out what's going on here, because I have a lot of these AND gates here, and I'm wondering if they're just using those as buffering. So let me just scroll down real quick because you can see it all here. It'd be interesting to know. I'm wondering if these are designed to protect the WROVER chip. So pardon me. So as you can imagine, you could sort of mess with the signal on the SPI bus here, and you could cause all sorts of problems. It suggests to me that they're doing something with these, because I think if you've got the SPI signal plus a constant 3v3, so that would be a 1 plus that. If that is an on, then it's going to output a 3v3. So I don't know if it's converting from something, but I think the WROVER chip is 3v3 anyway, so I'm guessing it's a buffer. If you have any idea of why they've done that, let me know. Again, I kind of think it's to stop bad signals jumping in here and messing up the bus, because the screen is connected to the SPI bus and you could get all sorts of interference going on in the screen. Let's zoom back out again and see where we are. So let's cover the Dpad. The Dpad is here, so you can see that's nice and simple. You've got a 3v3 supply going to one side of each of the switches. And when we say switches, it's the wiggly wobbly copper track that gets touched by that carbon pad when you push down on the decontroller. And it looks like, to me, interestingly enough, you see how they're coming into two different inputs. So up and down are actually the same input, and then left and right are also the same input. So let's see what happens when you do that. So here's your point here. Let's just zoom in so we can see. So if you look at the test point, imagine that's where your CPU is connected, which it is. So these are, when you push down on them, they're being pulled up to 3v3. So the voltage detectable on test point 5, for example, is going to go up. So when you push down on up, it's going to go straight to 3v3. Yeah, it's going to pull up straight hard to 3v3. But then when you push down, it's going via a resistor, so you won't see 3v3, you'll see a different voltage. So it's obviously an analog input that's doing this, so it's discerning between those two states with analog. Interesting enough, if you push down and up at the same time, and I know you can't, you would register that as an up, because up would always short out the across the down. But that's, you know, like sometimes we instead of having a D-pad, you've got 4 separate buttons. That would register as an up in this case if you push the both, but it doesn't matter on this one. It does have a rocker. And then test point 6 is just doing the same for left and right. So it's interesting that they've done that. So they've saved themselves 2 I/O pins doing that. And again, we're going to cover the I/O pins a little bit later, because I've got a few comments to make myself on those. And then let's look down here. This is a slightly different arrangement, but not so different. So these are the buttons that are the menu, volume, select, start, etc. But these are wired in a different way. So what they've done here, looking at them, they're all going to different inputs here. So 13, 0, 27, 39, 33, 32, etc. And they're all being basically pulled to ground when you pull them up. So I'll give you an example using switch 5 because you can see that. You can see it's getting pulled up to 3v3 via a 10k resistor. So then when you push switch 5, it gets dragged down to ground. So test point will normally read, test point 12 would read 3v3, and then when you push down, it will read 0 volts. So when it's 0, volume is going, okay, they've pushed the button. But you see here, they've only done it on switch 5 and switch 7. And the reason is, I suspect, and if we check in the datasheet for the WROVER chip, that there's internal pull-ups on those. So a lot of microcontrollers and devices have internal pull-ups, so you don't need this whole separate 3v3 thing going on. That's just going to be handled internally in the chip. So they've had to add that because those two channels don't. And you say, why is the reason it doesn't have it? And the reason it doesn't have it is because a lot of the input outputs can be used for other purposes. So that could be maybe an I2C or some other bus system that would normally be on there. So you're not allowed to have those resistors in the circuit. So let's jump over to the screen, because the screen is remarkably simple. So if you've ever considered wanting to use one of these screens, now you can, because you can just see exactly how they're hooked up. Nothing too cumbersome really. You've got a 3v3 supply, so that's obviously power just running through, and you've got the VDD and VDD IO. So you've got the power to the screen, which is there, but you're going, oh, there's a VDD IO. That's probably because the screen could support a 5-volt bus as well. So remember, you could have your SPI and I2C and all your various buses either running at 3v3 or 5 volts, depending on your standard you're using. So this module appears on its connector to be able to support two differing buses. And likewise, you can see here you've got the LED. So you've got the anode of the LED connected to 3v3, and then you've got the cathode here connected to ground via this transistor, and we'll go into that now. But you can see basically you could drive the LEDs even at a different voltage, because they're again kind of a separate thing to the main body of the screen. But while we're on the subject, let's cover the LEDs, and you can say, why is it going via this transistor? And the reason is this can control the amount of power those are getting, and then that will affect the brightness. So there's two ways it could do it. Either you could vary the amount that's going on in this transistor to hold it in various different states, which I think is not what's happening here. What's happening is it's doing a pulse width modulation on transistor Q1 here, and that's basically changing how long it's allowing the LED to sync current to ground through this junction here. So if you pulse it very quickly, the screen becomes brighter to the point where you just keep it held on. That'll be the brightest setting. And then the darkest setting, you're kind of going bam, 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 bam. Do you see what I mean? And the human eye is not seeing those transitions. But if you hold it in front of maybe a camera or something and the frequencies start mismatching, you might see it flickering. I don't think we saw that when I tested it, but you never know. You find the right frequency. So you've got a reset line. There's a generic reset line, it seems, that runs through this board. You'll see that again elsewhere. You have DC. Now I do not know what DC is. If it's some sort of a reset or something like that, or chip select, there's something going on with that. Again, we don't. Again, I don't know what it is without looking it up. But it's probably not a chip select, because you have here VSPI CS0. So there is a chip select here going into CS. So if you know what DC is, please feel free to say it down below. So you have your MOSI, master out, slave in, serial clock, SCK, and then you have your master input, serial output pin. So look, that's basically all these things mean. Interesting enough, this MISO, where's that going? See, we can see the MOSI coming in, we can see the clock, but is the chip select also being serial? So it's a bit weird. Either way, all you need to know is, though, it's SPI. It's a SPI bus device, and it's being driven straight from the main CPU. And if you've got any gadgets that use SPI, you could drive a screen like that. Just copy that circuit right there. Just cut and paste, and you're done. Interesting enough, remember we were talking about these AND things. I think, interesting enough, you can see here, this is your this is the AND logic we were talking about, and you can see the SPI coming into here. But surprisingly, you've got a IO12, so it's using a different pin than this one. This has got IO21 doing something. Very, very odd. I have to sort of look into that a little bit more, see what's going on there. But you can see the VSPI MISO going on again on pin 7 there. VSPI MISO. Interesting. Right, let's go on to the next page now. The USB to UART, that's interesting because it's a bit like the old FTD 232R or 232I chips, or the Cypress. There's a lot of them. There's a whole bunch of them. But basically, they're a small microcontroller that can take USB. They've got a little USB serial stack, and then they provide normally RX, TX, and a bunch of the old school USB serial pins, rather, the RS232 pins, like you can see here, DCD, DTR, DSR, which most things don't use, to be fair, but this does use them, and I'll tell you why in a moment. And what it does, it takes the USB signals from that USB port, so you can see the D plus and D minus like we saw before, and V bus and all of the various things, and then it spits out these ones, and these are the ones we're using. We're using DTR, RTS, RX, and TX, so receive and transmit, and then DTR and DTS. And they stand for, what is it, data terminal ready, and I don't know what the RTS is. They're old school stuff. And then you have this interesting thing here, reset coming in, and that's being pulled up there. Keep that chip out of reset. And they're not connecting any other GPIO. And that's because you can actually use these in different ways. So they are they're quite funky, these USB to UART pins, chips. They do have a bunch of additional stuff in there that we never use, but you can, because they are a micro, and they will talk over USB to the host if you've got the right software. So some of those softwares, by the way, let you rewrite the driver, so you can actually control these in interesting ways. So one way you'd use these GPIOs is to facilitate the reset hardware on your module, because you might want USB, because these modules basically can be reprogrammed their firmware via serial, but we're using a USB to serial chip. So you go, how do you twitch all those other pins you need? Because normally they won't go into programming mode without the sort of weird Control Alt Del type key press in hardware, and you could use GPI to do this, but what they've used this DTR and RTS because not many other things actually use them. And you can see down here they've got these two transistors that are being driven from that. So you can see there's a weird combination between reset and IO0 that clearly are the programming lines on the ESP32 WROVER chip, and they're being handled by this DTR and RTS line. So that's what they've done with that. So that's cute. It's nice they've done that, because it just means you can never brick it. In other words, no matter what you do, you'll have a way of getting out of it, and you don't need to go rooting around inside the hardware to find those RX and TX lines. So this brings us on to the chip itself. The top right corner, by the way, this is your SPI bus, and it's just a bit of nomenclature inside the design tool to show you that this VSPI block is actually a bus containing all of those lines, and the same thing going on here with this IO just above my head in the video. So the ESP32 WROVER chip, so this is the bad boy that does everything. And here's that reset line again coming in. Woohoo! That seems to sort of do everything. Generic board reset. So obviously fiddles with that itself as well to reset the screen and things like that when it needs to. And then you've just got a bunch of GPIOs here, and there's a few of the multiplexes going on here. So you can see that IO1 and IO3 are also the serial RX TX pins, and then on the left you've got something called sensor VP, which is IO36, and sensor VP, another one, IO39. So some interesting stuff here. So that's how you can tell, if you look on the bottom right corner where you've got three disconnected things here, that the I2C bus is disconnected. So the SDI, SDO, SCK, CLK, sorry, they're all basically not connected. So that's a weird one. I don't know why they did that. I did say I have gripes with this. I would sort of suggest, because you've got a board here that's so big, you know, it is quite a big PCB, and there's not a lot going on, because you can imagine a lot of it's spent just running tracks to these buttons, which is not much going on. You know, it's just simple tracking. Why not work out a way of getting additional GPIO onto this header? Because you could see on the earlier design you've only got actually 2 pins of IO on this, and then you've got the SPI bus, so it's all getting eaten up. I know you can probably get I2C by bit bashing in the SPI, but why not just bring it all out? Bring it all out. You've got 6, 7, 8 pins here, 8 IO pins you could have had just to extend that out, or just make it a double header. Don't know why you didn't do that, guys. Anyway, let's not dwell on that. So you've got the power coming in, this 3v3 power supply, going through a few capacitors to sort of take out any ripples. Interestingly enough, IO36 is also going to ground via a cap. I wonder if that is just some sort of being used as a you know, an analog input to test battery voltage. Could be something weird like that. It probably is. And then you've got your reset pin down here. So look, there is a reset. It's being pulled up to power. You see here being pulled up to power via 3v3. So it sort of suggests things pull it to ground when they want to reset this chip. So reset's being sort of pulled high. Keep it turned off, as it were. And then you've just got a bunch of GPIO, so all these IO 39, 34, 35, and then some of these are additionally multiplexed, by the way, and also some are inputs and some are only outputs. So when you see here, you've got this little arrow. I'm going to zoom in a bit more for you. So you can see here IO 34, you've got an arrow showing this is an input only pin. IO 35 is an input only pin. But then IO 32, 33, 25, so on are actually bidirectional, so they can be configured in the hardware for their inputs or outputs. And that's really all there is on this. There's not much to see because this is obviously a pre-packaged module. There's a lot going inside this module that would make this a very complicated schematic, but you don't need to worry about that detail because they've taken care of it all for you. So you are running effectively two power supplies. You could have the USB as a power supply. You can have the battery as a power supply. So the USB is 5 volts. The battery is going to be 3.7 volts. Or is it 4.7? Let's see if we can... 3.7 volts. But our unit itself, the CPU, everything is a 3v3 volt unit. So it's trying to improve efficiency and simplicity. It's using a DC to DC converter. So that's a bit like your AC adapter in your house where you're putting your mains into something your phone can use. This is doing it from DC to DC. So it's taking a battery or input source that's bigger, that's a DC, and then putting it out to something it can use directly. Nothing to see here, really nice and simple. They've got this input. So you've got the V-bus and V-bat coming in here. They're running in here. Looks like when V-bus is coming in, it's probably disabling the V-bat via this MOSFET. Something going on here. Then you've got your diode here, so that's, I guess, your reverse protection, and then it's probably to stop V-bat putting power out on V-bus, so that the battery isn't trying to drive your PC's USB bus in the wrong way round. And there's a switch here, switch 1. I'm guessing that's our power switch, actually, of all things. Yes, it is. You can see it's your power switch, but it's actually coming into the enable pin of the DC to DC converter. So let's have a little look-see here. I don't know if we can see it through the shell. Not quite. But it means the DC... Oh, yes. There we go. I can see it. I think it's probably here, right in the middle of the board. So the DC to DC converter is basically the master power controller of everything on this board. And then it's coming out through here. You can see here out, and it's just jumping in straight into the 3v3 supply, and then a couple more capacitors to get rid of any noise, probably located all around that chip. And yes, if you look at the chips themselves, you'll see all those capacitors right next to them. And some feedback here via this inductor, this 1 microhenry inductor, something like that going on. Again, FB. Your guess is as good as mine. Maybe that's feedback. Who knows? You can get the data sheets, by the way. Just Google MP2161GJ and you'll have a whole reference diagram over that, and it'll tell you exactly what it's doing if you don't know. Some of these things you don't need to worry about. This is probably just cut and paste straight out of the reference diagram. In fact, if you're bored, in the chat below, go have a look at the PDF and then you can tell me, is this literally cut and paste out of the reference diagram? I suspect it is, because that's exactly what I would do. So now we have also the battery charger circuit. So you've got that here. Do you remember this VBAT coming in here? This is where it's coming from here. But also you can see VBus has another purpose. So VBus is being used as part of this whole DC to DC malarkey, but it's also being used to charge the battery. So imagine it's split off at some point. You've got the VBus is splitting off. Half of it's going to the DC to DC and half it's going to the battery. And I say half. That doesn't mean anything in this context. Right, so here's the chip. It's really simple. Look, it looks like a little tiny 4-pin chip. Sorry, 4-pin as in maybe a 5-pin, maybe a 6-pin, but definitely at least 5 pins, because that's the 5 pins we can see. So the VBus is coming in. Again, you've got these capacitors here to take out any noise. you've got some, what's iSense, something sense. So it's something sense going on, but it's dragged to ground anyway. Maybe it's being used to detect if there's power coming in. And if power is coming in, you'll see a green LED come on, apparently. I've not noticed it, but must be one there somewhere, green LED. Look for that. And then this whole thing just handles the battery. You can see here it's got this battery output going on, and it's just handling it. It's just putting it out to battery. So it's taking this power in. It's doing whatever this thing for. It says charge. I think this is activating the charge when this is pulled high. So that's why it's going via this resistor, I think. And probably when it's done charging, this will stop pulling to ground, which will mean the green LED will turn off. I think that's what's going on there. Try it. See if the green LED goes off after a while. I think that charge is pulling to ground there. And then you have VSS pulling the whole thing down to earth. So that's just its reference there. So VBAT though has this interesting thing because again, that's the battery here, BT1. You can see the battery there, but also you can see that you've got this IO36 slap bang in the middle of this potential divider, 200Ks, and that's because IO36 definitely is being used for battery level monitoring. I thought I spotted something earlier that I suggested was battery level monitoring, but I'm pretty sure now it's that. Let's not worry about that. It doesn't matter. That's definitely it, by the way. That's definitely doing battery level monitoring. Cut and paste that into your own design. And then finally, we have the Transflash or micro SD socket here. And yeah, it's just nice and simple. You can see again the SPI lines hooked up. You've got CS1, which is this chip select one. You've got your master out again. You've got your clock and you've got your master input coming in. And that's it. That's all you need. There are additional pins here, like DAT1, you see. I'm not sure. There are interesting things with SD cards. I'm not sure if Transflash cards have them. They do have different modes. They have like a 1-bit mode, and they have a 4-bit mode or an 8-bit. It depends on the card. And they can do sort of fall back into various modes. And the hardware, the host hardware, is supposed to be able to communicate and negotiate these modes. So you can imagine they'll fall back on it. They have a very slow mode, and then if you say, okay, I've got more bits, and they can start pumping data out literally in parallel, and you can speed them up. But I think that's why you've got this sort of dead thing going on here on pin 8 and maybe pin 9. But why worry about it? Look, it's all just hooked up on SPI. You could hook up literally anything you want on this bus and then drive your own chip select. So if you've got, for example, top right corner here, so we know that we've got the bus going on here with this pins, let's see, pins 2, pins 3 clearly, and pin 7, and probably pin 8 from the look of it. You could do what you like. So if those are hooked up to SPI, you could use pins 4 and pins 5 as chip selects. Yeah, and then you could have a whole load of other stuff on SPI, or you could even have a SPI port expander that you would twiddle if you want to get real complicated. So yeah, you can do stuff with this. It's definitely upgradable, but again, I would have liked to see more of this I/O coming out in a more usable way. And of course, we don't have a standard sound out, which kind of sucks big time as well. I think even with mono sound, I would have still rather had a headphones with the mono sound that exists on this today. So hopefully it's been of some use to you, this whistle stop tour. As we're not sort of doing any main development of this, we haven't got all the data sheets for these. But remember, even where I've skimmed through it or I haven't even known something, I'd just jump in to find like a PAM 8304 data sheet or whatever a data sheet is for these. Look, NC7SZ08P5Xs, they're going to be, I bet you, they're just going to be little logic chips, maybe even one single logic, no, I think there's 3 separate ones here, giving you your ANDs. All of this stuff is readily available, and most of it will have reference designs. You can see how it's designed here in this schematic as blocks, so that's a block of stuff, That's exactly how I would do it, because you're literally cutting and pasting and building your product by inserting blocks of functionality, and as long as you hook up all of these address lines correctly, keep the nomenclature the same throughout your whole schematic, everything's going to hook up when you lay out the board. So comments down below. Please like, share, subscribe if you're that way inclined, and if you want to get in on the action in terms of developing and talking about this, please join my Discord channel. The links are down below. We've got an active community of hardware developers, software games players, and messing around people. Just come and join us, chat, come be one of us. As ever, thank you for watching.